Okay, in which case I'd like to introduce Jon Peddie. We're very honoured to have Jon Peddie here, one of the industry's leading graphics analysts, and he's going to give us an overview on how Khronos standards have been impacting the wider industry. Jon.
Good morning, and thank you very much for coming today. Hope this has been interesting to you. I'm always concerned that when we speak at these conferences, we take a little too much for granted. And so at the risk of insulting you, I'd like to make certain that we understand what an API is. And that an API is the software interface between the hardware and the application and the OS. It's a very, very critical piece of software that does the communications and the translation from hardware registers to the I/O function of the application. And so if you already knew that, I apologize. If you didn't, I hope that helped. So Jon Peddie Research, very briefly, is we are a marketing and consulting firm based in California. We track the industry. We like to say that we follow the pixel. Anything that has a pixel in it, we care about. We test various devices to see how they perform, and we do consulting and advisory work for the industry, for the manufacturers, and for the investment community. And somewhere in the presentation is my email address, and on your USB memories are some examples of our reports and things. And again, there is email contact in there. Afterwards, if you have any questions about the market or the industry or anything that you think you'd like to ask, don't be shy about sending me an email. I answer all emails. Just historically, Cronus is derived from the god Cronus, and the god Cronus was the god of time. He managed time, he controlled time. And time is the biggest problem that we have in the computer industry and in the electronics industry as well, in that we just don't have enough of it. And so we're always under pressure to get things done, to get to market sooner. And the reason we're under that pressure is because there's a lot of competition in the market. There's a lot of very smart companies, and they're doing clever things, and as participate in the industry, we want to try and get to the market before they do, or at the very least the same time they do. And that creates a pressure on the developers, and the tendency can be to take an easy route and avoid standards, because standards are complicated. They require you to abide by certain laws and certain rules, and if you just ignore that and do it the most expedient, the fastest way, you can maybe save a few days, maybe even weeks in getting your product to market. And that might work. In fact, it actually does work. And that's the bad news, because you can get to market, but then when you want to develop your second product, you have difficulties, because typically when you take shortcuts, you make mistakes. And so if you make the mistakes in a non-standard environment, you're all on your own. You have no help from the industry. You have no help from anybody else. You have to fix it. And then when you make your second generation product, you have to carry those problems forward with you. And so it just compounds itself, and it makes life very, very difficult as you go forward. And there's some classic examples of companies who have suffered greatly from this and ended up going out of business. So Cronus recognized this problem early, about 10 years ago, in fact. Cronus is now approaching their 11th year. And the Cronus people came together to establish some standards that would help avoid the trap of getting into proprietary systems. Now, Cronus came up with this crazy idea that they were going to offer these standards for free. And this might be a little difficult for you to imagine, but if you could imagine 10 years ago, a bunch of guys going out to various companies and saying, hey, we got this great idea, share your IP with us, and we won't charge anybody for it. Well, that obviously didn't get a whole lot of warm reception in the early days, but a couple of people liked the idea, they could see the logic of it, and they signed on and they started doing some work together on it. One of the first products that Cronus was able to come out with was a stripped down version of the popular API called OpenGL. OpenGL had been developed by Silicon Graphics about 20 years ago. And Tom's going to tell you a whole lot about that. But OpenGL was the most powerful API, still is the most powerful API, but used for bigger machines, workstations, and things of that nature. And so what Cronus did is they said, look, we can see what's happening in the mobile phone business, and we have got to get there time and get an API in there now before this market runs away. And what better API is there than OpenGL? So they made a stripped-down version of it. They called it OpenGL ES, which stands for Embedded Systems. A mobile phone is an embedded system. And so that was the beginning of Cronus's development. And it was a very, very successful development, if I do say so. Now the issue here is, and this was very, very predominant and obvious about 10 or 11 years ago as the mobile phone market was starting to take off, the issue was there were different processors, there were different OSs, and if you were, let's say, an application developer, and you wanted to write an application for one phone, well, you could do that. And it would be wonderful, and you would then try to get your application on another phone. But the problem was the clock was still running, and time was moving on, and by the time you got to the other phone, it was probably already obsolete. So you're always playing catch-up, moving from phone to phone to phone with your application. The alternative to that is if you were a bigger company and you had a large staff, you could have a development team for each phone working in parallel. But that's very, very expensive, and so not many companies could afford to do that. So the obvious answer was to have a standard API that would allow you to write the application once and play it everywhere on every phone that complied with that API. And that's what OpenGL ES did for the market. Now the fact that OpenGL ES was successful and that the business plan of Cronus was acceptable is proven by the fact that Cronus has been asked to develop more applications. And they've done that, and they've done 15 applications now, 15 APIs. Now, Cronus didn't sit around in their offices and say, oh, we're not doing anything this afternoon, let's go build an API. All of these APIs were requests from the industry to solve the same kind of problem that the original popular API, OpenGL ES, solved. Now, they wouldn't have asked Cronus to do this if it wasn't a good formula, if the teamwork wasn't good, if the specification wasn't good. So the 15 APIs that Cronus has since developed, I think, is the most positive proof that you can find that they've got the right formula, they've got the right kind of business model for the industry. And the other proof of it is that OpenGL ES, as an example, has been adopted in not just one very popular OS, but in all these OSs. And the point to be made there is the companies that are developing and managing those OSs are large international corporations. They don't make silly decisions and they don't make dangerous decisions. So if they've decided to go with OpenGL ES, which they have, that means it's pretty rock solid and that they're confident that they can do that and get their business moving. Now the results of it in terms of market is there are two effects. The first is that, I don't know if you can even see this, this is the number of shipments of mobile phones in 2006. And back then, OpenGL ES had very little penetration into the mobile phones. All the rest of this stuff was proprietary. And over time, OpenGL ES became more and more deployed into mobile phones and smartphones, to the point where our projection right now is that by 2014, 100% of the smartphones will be using OpenGL ES. Now, I believe that this projection is actually too conservative, and I think we'll hit it in 2013 easily, because we're so close right now. There's just a very, very few companies that haven't adopted OpenGL ES. And then going forward, it's just done. But look at this. In the case of the tablet, which basically hit the market thanks to Apple in 2009, 100% deployment from the beginning. Further proof that OpenGL ES is a very, very good standard, one that you can rely on, one that has a lot of support. Now, why are these APIs that Khronos develops so popular? What's the magic? And the magic is, it's the way the organization works. The organization invites its members to come to meetings, and they meet in rooms just like this, some a little bit smaller than this, and they discuss all of the issues that are involved in the specification for an API. Each member of the team has one vote, and each member is there for two reasons. Reason number one is the member from company A doesn't want the member from company B putting something in the specification that would lock out company A. Reason number two is the member from company B wants to get his stuff into the specification, but has to do it in such an open and democratic way that company A will accept it. That becomes a win-win situation. When you first think about it, you think this is politically impossible, but it turns out that it works very, very well. The other part is that the people who come to these meetings are the best of the best. They are the best engineers in the companies that can send them. That's another example of the commitment that the companies make, is that they are willing to let some of their best engineers leave the office and go to these meetings to discuss these APIs. That shows you how critically important the APIs are to these companies, that they will send their very best engineers. But the other benefit that comes from that is these very best engineers, most of them have gray hair, I'm happy to say, these best engineers have been doing this for a long time. They are very, very experienced engineers. And so they bring with them decades of experience and understanding and knowledge about the intricacies of the processors, the intricacies of the applications, the operating systems, etc. And that type of knowledge, multiplied by all of these people who participate with the give and take that goes into it, means that when they are finished, that API specification is as close to perfect as you can find. And that's another reason why the APIs from Khronos are so well accepted and so well proven. And it's also another reason why the membership list has grown to such size. I don't know if Neil mentioned the number or not, but I think it's up to 113 now, and it's growing regularly. There needs to be more Chinese companies in this process. Khronos has recognized the problem. That market growth that I showed you, the growth of the smartphone market was largely enabled as a result of OpenGL ES because of the cross-platform compatibility of the applications. The fact that you could go buy Angry Birds and play it on your tablet, on your mobile phone, throw that mobile phone away, get a new mobile phone of a different type, and still play the game, that's the cross-platform capability that the OpenGL gives you. And that's what brought consumers to the market in such large numbers, is they knew that if they bought a mobile phone and an application, it wasn't a one-time situation and they were done, that they could continue to have the enjoyment of it going forward. The growth of the market, however, has created a new problem, and that is we need more engineers, lots more engineers, to develop the applications and to develop the APIs and to keep the market steadily growing. And to that event, Cronus has introduced a program called KITE, and later this afternoon there'll be a discussion about KITE. One of the things that we hope to accomplish at the university here is to attract professors to be sponsors and chairs of the KITE program to help train folks like you on how to use these APIs and applications. So I think that's all I have to say, and well, I got ahead of myself, didn't I? Anyway, so KITE. You've heard that. So come to Cronus, join Cronus. It's an international organization. The APIs are wide open. They're free. That's the best part, I think. Well, one of the best parts. and they need your help. And we definitely need to see more participation from China. Just a little side note, I may be repeating something that Neil said, is that there are companies in China who are using OpenGL, and that's fine, we want that, but they are not contributing to it, which means that they are denying themselves the opportunity to influence it. And that's the message we've got to get out to the Chinese industry is, here's your opportunity to control and manage these specifications rather than just being a user. So that's it for me.
So today I'm talking about the OpenGL family of APIs. The purpose of OpenGL family is to provide 3D graphics on all kinds of platforms. Starting with the original OpenGL, which is the leading standard for cross-platform 3D on desktop type platforms, workstations, PCs, consoles. More recently, of course, my own work concerns mostly OpenGL ES, which is a subset of OpenGL for mobile devices. Found today in hundreds of millions of cell phones, of increasingly also digital TV, consoles, automobiles, that kind of device. The most recent OpenGL API is WebGL, which is binding of OpenGL ES for JavaScript in HTML5. Today I'm going to talk mostly about OpenGL and OpenGL ES, the new features of OpenGL, and some practical issues if you're an engineer writing programs for OpenGL ES, some of the issues that you need to deal with to write portable code. I'm not going to talk about WebGL. It's very new in the market and there is not much application experience today. Neil will say some more about OpenGL later on, about WebGL later on. So we'll start with OpenGL. This is a very important year for OpenGL. The API is 20 years old this year. The first version was released in 1992. Graphics has changed a great deal in 20 years. The API today is very different from the original API. Since 2008, OpenGL has been progressing very rapidly. For a long time, change was slow, and this was a problem because Microsoft DirectX became bigger, a better feature set, more powerful. So in 2008, the OpenGL working group decided they needed to improve, so they went on a very rapid development cycle, releasing a new API every 6 months until the most recent version, OpenGL 4.2, which was released at SIGGRAPH 2011. With OpenGL 4.2, OpenGL now has the same feature set as Direct3D 11. So all of the features available in Microsoft land are also available in OpenGL land. So this is an important milestone. This means that even the most advanced desktop content, such as the Heaven benchmark from Unigine, can run in OpenGL mode. So I want to talk a little bit about what is new in OpenGL 4.2. This is a technical presentation. I think you are all, many of you engineers or students or professors, and so this should be appropriate content. The biggest, most important feature in OpenGL 4.2, and also the biggest technical trend in desktop graphics, is the integration of computing features into the graphics API. So with OpenGL 4.2, we now have the ability inside a fragment shader or a vertex shader program running on the GPU to both read and write to texture memory and memory buffers. This creates some interesting problems because now it's a parallel computing environment. Within a GPU, usually you have thousands of threads running, and if they're all writing to memory at the same time, you will have race conditions. So you need to think like a parallel programmer. To help with this, we have another feature, which is atomic counters. This gives you atomic read, modify, write operations to memory. So multiple threads can read a value, increment the value, or add to the value, and have consistent results from all threads, even though there is no synchronization between them. This is powerful functionality, but it's very limited. It's important to realize that this does not replace OpenCL, which is Khronos API for general purpose computing using a GPU. So if what you want to do is do a big physics simulation, water simulation, any kind of physics, and then render the results, it's better to use OpenCL for the physics and then use OpenGL for the rendering. But what these new features give you that OpenCL does not have is the ability to combine computing and graphics in a very tightly coupled, close fashion. I'll give an example of this in the next slide, the kind of thing that this allows you to do. I will mention the other features. There are many. One of the more interesting is immutable texture objects. These are textures where the size of the texture and the format is frozen at creation time. So this limits the application's freedom, but it's very useful because it means that the graphics driver can be much more efficient. So this helps performance if you can use immutable textures. Instance transform feedback allows you to capture the results of instance drawing calls. So you make one drawing call that draws multiple copies of an object with different state, and capture that into a buffer which the CPU can examine, or which can be used for multiple passes of rendering. BPTC texture compression is the new compression formats from DirectX 11. Again, we say we have now all of the features of DirectX 11 are available in OpenGL. And shader language packing is a feature which helps, again, with these computing features. It's the ability to put multiple 16-bit or small values into one word to save into memory in using either in a memory buffer or a transform feedback buffer. So I won't talk more about those new features. They're useful, but they're small. But I want to give an example of how you can use the computing features of OpenGL 4.2 to do something which would be very difficult using the older versions of the API or using OpenCL. So we will look at a classic problem in computer graphics. You want to draw transparent objects on the screen. I'm sure you all know you can use alpha blending. That gives a good impression of transparent appearance. But the mathematics of alpha blending require that objects be drawn in order from back to front. If you draw in the wrong order, you get the wrong result. So for example, if I draw red, green, blue, I get this appearance. If I draw the same objects with the same alphas in a different order, blue, green, red, I get a different result. So correctness depends on correct drawing order. If the CPU has to decide the drawing order, this is very expensive because the depth depends on camera position. There's a lot of work done by the GPU to save the CPU from this work. If the CPU has to sort by depth, that's a problem. So we don't want to do that. That leads to a problem we call order-independent transparency. How can we draw correctly so that the application draws in any order, but we always get the correct result in terms of the transparent layering? There are some classical approaches in the literature. If you have studied computer graphics, you know this. Depth peeling is a popular one, but it requires a pass for every transparent layer in the scene, which is quite expensive. K-buffer is another approach, also expensive. So we'll look at a very simple new approach that uses the new compute features of OpenGL. The basic approach is we'll render all the objects in any order, so the application does not have to control the order of the objects. And the fragment shader that renders these objects will collect all of the fragments. So for every triangle, for every pixel, we'll collect a list of the color values and depth values in any order. And then at the end, we'll do a post-processing step where we collect all of those, sort them, and do the compositing. All in the GPU, the CPU has nothing to do. So I'll illustrate this with an example. The way we do this, we'll keep one array which is an integer texture, which is of the size of the whole image that we want to render. I've shown a small one here. And this array will store the number of valid fragments, that is, the number of layers at each pixel. So initially, this is 0 because we have not drawn anything. So we initialized this integer texture to all 0. Then we have a bunch of layers which store for every pixel a color and a depth. And what we'll do is every time we render something, we'll record, well, I'll show how this works. So suppose I draw a triangle which covers this pixel. I can use the atomic increment capability from the new OpenGL 4.2 compute features. To read this value, it tells me there are 0 fragments at this pixel. That is, there's no information currently stored. So it gives me a 0, and it replaces the 0 with a 1. So the 0 tells me, store your color and depth in layer 0. And the count is automatically incremented to 1. If I draw another triangle that covers the same pixel, again, when I read this value, I get 1, so I store my color and depth in layer 1, and the count of fragments is automatically incremented to 2, and so on. So when I finish rendering all the transparent layers, for every pixel, the count tells me how many colors and depths are stored, and they're stored all in the layers in some order. Then to finish the computation, I do a post-processing step where I render a single triangle that covers the whole screen, and in the fragment shader for that triangle, I read the count to tell me how many colors are stored, and I sort them by depth, and I render the last one, then the next one, then the next one. So I always get correct results, and it takes only one extra pass. This is more efficient than depth peeling generally. It's more efficient than K-buffer. This is, of course, a simple approach, and there are some ways to improve it, and there are some problems. You could, for example, decide that instead of storing the colors in the order that they are drawn, you could sort them as you insert them using some kind of classical computer science insertion sort. The problem is that each one of those layers in the texture is the size of the whole screen. So if you have 100, memory's full, you can't do anything. You can really only have perhaps 8 before you will run out of memory. So what do you do if you need to draw more than 8 layers? Well, you probably know if you draw many layers of transparent material, really only the ones in front are important. The ones in back are not so important. So it's okay to approximate. You don't have to be exactly correct. There is some very nice academic paper from HPG 2011. If you look this up on the internet, Salvi, Adaptive Transparency, gives a very nice solution to doing this kind of computation using the same capabilities, but approximating so that the number of layers can be limited. So that ends what I wanted to say about OpenGL. I want to talk now about OpenGL ES. I'll talk first just about where is the API in the market today, and then I'll talk about some technical issues. OpenGL ES is the leading 3D API in mobile devices. It is standard in Android. It is standard in iOS, on the iPhone and iPad. It's standard in various mobile Linux variants as well, Linaro, for example. It is used in these APIs not just for games, but it is also used for the user interface, for compositing windows together to render the screen. And it's used both by the system for, as I say, window system compositing, and it can be used by applications or browsers to do compositing within the application. I, of course, have been working on this for many years. It is close to my heart. This year is very exciting for me because in the last year, we have finally begun to see some of the most sophisticated graphics software in the world. Game engines such as Unreal Engine 3, the Unity engine, other game engines are now available on top of OpenGL ES. And because of that, we now have major game companies creating very sophisticated content and charging good prices for it. So this, for example, Infinity Blade, and this is the Rage demo from id Software. This is satisfying for us because now we have a way to go all the way from the consumer who wants good content, good games, good applications, all the way through the pipeline. All the pieces are complete. So we have a strong economic system. And this is what we have been working for the past 10 years. So it's very, very satisfying. The working group today is concentrating mostly on next generation. Our current API is OpenGL ES 2.0. That's the one that was used for the content that you saw. We are working on another version of the API. It is not ready yet, but we are getting close. And when we see the market demand is there, we will release it. Another activity that we have going is that we're working very closely with the desktop group for OpenGL to make desktop OpenGL and OpenGL ES more similar, so that it's easy to bring applications from mobile devices to desktop, from desktop to mobile devices. This, again, we think will help applications programmers to have a more rewarding ecosystem and be able to produce their products with lower cost. I'm going to switch now and talk about some technical issues for the next 20 minutes or so, 25 minutes, in OpenGL ES 2. And my topic is mostly about portability. So the question is, how do you write an application in OpenGL ES 2 that is portable across lots of different implementations? So we'll look at a couple of questions. The first one is, why is this a problem? OpenGL ES 2 is a standard. Why is there a portability problem? It turns out there is, and I will explain why. Then we'll say, what are the barriers to portability? What are the things that can cause your application to be not portable across implementations? And how can you avoid this? These are my opinions. They are based on talking to a lot of developers, so I will defend them. But I'm also interested, if you write code for these APIs, I would like to know your experience. Please talk to me. Also, I'm giving an introduction to this subject. It is actually complex, and there will be issues that I can't cover. We probably, in fact, will not cover all this material today. So first, why is portability a problem? Why is this not a solved problem? We have OpenGL ES 2 on all the platforms. That is, it's on iOS, Android, WebOS, Symbian, Linux. So if you write your code to run using OpenGL ES, you would think it's portable everywhere, but in fact, there are problems and it's not completely portable. And this is not an accident. There is a reason for this. So we'll see what that is. When Khronos sets out to design an API, we are not just defining what are the functions you can call and what do they do, what are the results of those functions. We are actually trying to design an economic system in which the people who produce the hardware, the people who produce the software, the applications, and the people who own the platforms in the middle all have an opportunity to make money. So if any one of them makes no money, the whole system is broken, because no one will make money if there's anybody who is cut out. So we have to have a way to share. So if we look at one extreme, suppose I build an API which imposes few restrictions, which allows many different implementations that behave differently. The most extreme case would be, suppose I let every hardware developer develop their own API, which is different from every other hardware developer. Then I'm in this space here. This allows the hardware developers to innovate, to advance their technology very quickly. So you have very rapid progress of the hardware technology, but the software people cannot make money because it's too expensive to write applications for all these different hardwares. So the result is, I've here plotted flexibility versus portability and ecosystem strength, economic strength. If we're in this space, the economic strength is poor because the software developer can't make money. At the other extreme, we could make an API which completely defines everything that the hardware must do, and no one is allowed to do anything different. This is, for example, what you have in a console, where a game console, all copies of the game console are identical. That's very good for the software developer. They can optimize very well, and their development cost is low. The problem is that the hardware vendor can't make money, and the technology cannot improve, because if you add features, you are not compatible anymore. So what happens when you do this is that the hardware vendors save their best ideas for some other platform, some other API. So this API works well for one generation, and then it dies. So this model is also not good. What we try to do in Khronos and in OpenGL ES is to have a middle road where we allow some freedom so that the technology can improve and the hardware vendors can have good ideas and exploit them. But also there's enough portability and enough consistency that software developers can live with the variation. It's always a trade-off, and it's always causes a lot of discussion in our working groups. But this is why we do not have perfect portability in OpenGL ES 2. So now we'll look at what are the kinds of differences you can see between OpenGL ES implementations from different vendors. First and foremost, of course, you will see performance differences. Some people want to spend more money and have a faster device. Some want to spend less money and have a slower device. There are also differences, places where the OpenGL ES specification allows freedom in how much resources you provide. I'll give examples of those in a minute. And that those are permitted by the specification, but they do create some portability issue for software. And then finally, the API provides a mechanism for hardware vendors or implementers to say, I have a new feature which belongs to me, and I can expose it through an extension, which is an addition to the specification, which possibly only I support, or possibly some vendors support and others do not. So first, let's talk about performance. Many differences in performance are due to details of the way the software driver for the hardware works. So it's very common, for example, if you're a computer scientist trying to have a high performance device, very often you will defer work. It's always good policy not to do work until you need to do work. So for example, many hardware implementations of OpenGL ES use what's called tile-based rendering, so that when the application says, please draw this geometry, the hardware will take this geometry and instead of drawing it, it will save it in a database, which is indexed by screen position. Then when the application says, please give me the final image, only then does the hardware actually draw the geometry. This leads to there is a reason for this. It gives higher performance overall and lower memory bandwidth. But it also changes when work is done. So if you are trying to determine, for example, by timing a function call, how much work is the system doing, you may be fooled because the work may not be done when you ask for it. It may be done later. Many implementations also do this with texture data. If you give GL a texture, if you give GL pixels and say, please make a texture with these pixels, it may happen when you ask for it, or it may not happen until you try to draw using those texels. Compilation speed for the shader is another issue. When you deliver a shader program to the API and say, please compile this, it may compile it when you ask for it, or it may compile it later when it believes you are not busy, or the CPU is not busy. Other driver issues, among the implementations of OpenGL ES, some have very fast compilers, some have quite slow compilers. In some implementations, if you change some kind of state, for example, if you change the blend state of the hardware, that may cause the shader program to be recompiled if the hardware is doing the blend, if the shader program is doing the blending. Other implementations don't do that, so you will see differences in behavior because of that. Draw call overhead again, just differences between implementations.